Okay, can people hear me?
Yep.
Excellent. So today is the Student Choice Day. It's going to be much more like, a standard lecture because we don't have problems to solve on this. So the first part of this is put together nicely, and it sort of peters off at the end because I ended up getting an awful lot of questions today during office hours, so I did not finish. I've got slides, which is unusual for me, but I didn't finish the last few slides because I was answering lots of questions about the homework, which is a good reminder that you have a homework due on Wednesday, right? So today is our last sort of class meeting with material that we're covering. You have your last homework due Wednesday at 3:30, and then Wednesday at 3:30 we'll have like a little review session. We'll talk about the final exam a little bit, talk about solutions to any one of the homework problems that you'd like to see worked out, and then that's what we'll do on Wednesday. Then there'll be the final exam. Let me look up for just a second here and see when the final exam is Wednesday, May the 6th. So that's actually a week from Wednesday, right? So we'll have the review and then the exam is a week later. What we can do, if you'd like, is have another review session like on the 5th, right, on Tuesday. And then you can ask more questions as you're, finishing up preparing for the exam. So both of those days, both Wednesday, I'll have a few things prepared on Wednesday to talk about, just sort of explaining what to expect on the final exam. But for the most part, it's going to be just a review session, problem sessions, but anything you want worked out. By that time, you will have worked through all the homework questions and either gotten them and you don't have questions, or you've gotten very frustrated and you want to see what a solution looked like, so we can go through those. I think that's it as far as announcements. Does anybody have any questions? Okay. Then the topic for today is cryptography and how cryptography relates to theory of computing and some of the things that we have talked about. Let me get these slides pulled up. Hopefully you see that, right? Good. Let me sort of scoot these windows over. All right. So what I'm going to do is we're going to talk a little bit about cryptography. And what I hope to show you is that modern cryptography would not exist if it wasn't for the things that have been developed for theory of computing. The things that we have talked about, understanding different time complexities and P versus NP, right? Non-deterministic polynomial time versus polynomial time. That is very central to cryptography. The notion of reductions that we use in theory of computing, how you relate the complexity of one problem to the complexity of another problem, or even the decidability of one problem to the decidability of another one. That's also central to how cryptography is done these days. So this is what we're going to talk about. We're going to talk about the importance of the P versus NP question for cryptography and how it depends on that. Then we have to do a little bit more background on sort of formally how we define what it means for cryptography to be secure. There's a lot to that and a lot of subtle things that go into how you define security, lots of different variations of that. So I'm going to keep it as simple as possible just to give you a feel for how cryptographers do that kind of thing. And then finally, we're going to see how once you've defined security in a certain way, you can use reductions to reason about the security of different cryptographic algorithms, different cryptographic protocols over a network, and that sort of thing. All of these are used in a very important way in cryptography. And if these ideas hadn't been developed, then we wouldn't have cryptography as we know it today. In fact, one of the main enablers of sort of the modern internet and e-commerce, buying things securely online, doing secure banking online, all the things that we kind of take for granted these days that depend on cryptography, depend on certain kinds of cryptography that were first thought of in 1974, 75, something like that, called public key cryptography. And public key cryptography only came about because of the work that people had done in 1970, 71, 72 on NP completeness. That got people thinking about how you compute functions in a different way. And it was that insight into what it means to compute things and to compute things efficiently that led to public key cryptography and led to like Jeff Bezos being the wealthiest person on earth, right? So that is where we're going. And since this is not a problem session, I don't have really places to stop in here and pause and ask questions. So if you do have questions at any point, I've got the chat window open here. I'll see if you send a chat, or you can, raise your hand in the participants window. I'll see that too. So, feel free to stop whenever you have a question about this. All right, so first some basics. What do we mean by encryption? And this is the picture that I want you to have in your mind. Let me see. That's not what I want. I want to see if I can get like a pointer or a highlighter. Can you see this sort of highlighter moving around?
Yeah.
Good. All right, so This is the basic problem of encryption. So the sender of a message is over here on the bottom left, right? They want to send a message over a network, an insecure network, to a receiver who's over here on the bottom right, and saying you want to pay your bill and you're giving a credit card number there, okay? Now, this is going to go over the network up here. This is, in general, in crypto, the generic term for this is the channel. This is the communication channel up here. And this little evil looking dude in the middle is the adversary. And this is an insecure network. So you've got an adversary in here that has access to the communication channel. Now the adversary can do various things. And so when we talk about security, we talk about different models of an adversary. Can the adversary, at the very least, the adversary can view every communication on the channel, right? So they can get a copy of everything. They can monitor that channel. That's sort of the weakest kind of an adversary. A slightly stronger adversary can intercept things, modify them, and send along a modified version. So those are the kind of things we talk about an adversary being able to do. So your original message down here on the lower left, and the model we have is that it will go through an encryption function. The encryption function takes two inputs. It takes this, which we call the plain text, right? This is the message that the sender wants to send. This is the plain text down here. Plain text goes into the encryption function with the encryption key. The output of that is called the ciphertext, right? That's the data that's to be transmitted. So the ciphertext goes up through some network interface out across the channel and gets received over on this side. Ciphertext comes into the decryption function. Decryption function also takes two inputs. It takes the ciphertext and it takes a decryption key, and the purpose of the decryption function is to recover the original plain text. So that's the basic model of cryptography. Now, cryptography these days, I suppose that's the original notion of cryptography that goes back many, many hundreds, thousands of years, right? One of the earliest encryption systems like this is called the Caesar cipher after Julius Caesar, right? I mean, so this idea goes back a long time. And this is what I think most people think of when they think of cryptography. And it's about keeping secrets. Cryptography these days, modern cryptography goes far beyond just protecting secrecy, right? So confidentiality means protecting secrets. These days, we have different forms of encryption for protecting integrity, making sure that things aren't tampered with, for example, or making sure that a message comes from whoever claims that it's coming from, right? So if your credit card company sends you a message, you'd like to know that that actually came from your credit card company and not somebody trying to scam you out of your credit card number or something like that, right? So that we use cryptography for that. You can get much more complex, and you can use cryptography to protect the integrity of transactions. And that's what blockchain and Bitcoin are, right? So, I mean, that's cryptography. But it's not about protecting secrets. It's about ensuring the integrity of financial transactions. So cryptography goes far beyond what I've got here, but this is good enough for us today to just sort of get the ideas of how we use concepts from theory of computing for this. Given this basic picture, the questions we might want to ask, notice I refer to the encryption key and the decryption key. And so for the hundreds of years up until the mid 1970s, every encryption scheme that was developed basically had the same encryption key and decryption key, right? So this was a secret that was shared between the sender and the receiver. And so, if you're talking about a military model on a battlefield, right, where one unit in an army is sending messages to another unit in the same army, what happens is they share some secrets. They share a secret key before one unit deploys somewhere else, and then they can communicate secretly, because they have this shared secret between the two of them, and then the encryption and decryption keys are the same. In 1970, when we realized we could do much more complex things with computing, it became clear that you didn't actually have to have the same key on both sides. You can have different encryption and decryption keys. They obviously have to be related to one another, because the decryption key has to recover the plain text that was encrypted with the encryption key, but they don't have to be the same. And in fact, it doesn't even have to be, they don't have to be related in a way where you can easily compute the decryption key from the encryption key. You want that process, if you can compute the decryption key directly from the encryption key, you want that to require more than polynomial time. But that's the first basic question we ask. Are the keys the same or are they different? They can be different. And so when we talk about security in general, we focus on this key over here, the decryption key, because that's what allows, right? The attacker has access to the ciphertext. So they have one input to the decryption function. It's the decryption key that has to be secret, or else the adversary could compute the plain text themselves. So this is the important key for us, the decryption key. You can ask, what can the attacker do? Part of this was what I said earlier. Can they tamper with messages or just modify the messages? But we also talk about how much computational power does the adversary have, right? So if you're thinking in sort of real computer terms, as far as the computational capabilities of the adversary, you might think about whether your adversary is just somebody trying to cause problems that has access to a PC, or is it somebody in the National Security Agency that has a whole basement full of billions of dollars worth of supercomputers, right? Those are very different capabilities for two different adversaries. But in the science of cryptography, that's not the way we think about things. The way we think about things as we talk about the algorithms, the processes that the adversary uses, and then we limit those to be polynomial time, because polynomial time means efficiently computable. That's something that an attacker can do in a reasonable amount of time. And then lastly, what do we mean by breaking a system? And so let's formalize some of these notions, and then we'll talk about answers to some of these questions. So the first step is to formalize the terminology, the functions, the data at the various parts of this. So we talked about plain text and ciphertext, what they were in that picture, but how do we define those formally? So plain text are just strings, binary strings. They're strings of zeros and ones. Ciphertext messages are just strings of zeros and ones, right? Everything's bits in computers these days. So everything's strings of bits. Plain text messages are M1 bits. Ciphertext messages are M2 bits long. In some, although no secure systems, in some systems, you might think about, the ciphertext is the same length as the plain text. You put in 100 bits of plain text, you get 100 bits of garbled ciphertext out. In practice, ciphertexts are slightly longer than plain text for technical reasons, but a fixed length longer, right? So a ciphertext may be 128 bits longer than a plain text, for example. So that doesn't matter if your plain text is 1,000 bits, you still add 128 bits when you convert that to ciphertext, or if it's 1,000,000 bits, you still add 128 bits when it goes to ciphertext. So the M1 and the M2 can be different. Obviously, I say obviously, maybe this isn't obvious, but certainly M2 has to be greater than or equal to M1, right? You can't represent M1 bits of information in the plain text in anything less than M1 bits in the ciphertext, or else you'd be losing information when you transmitted it, and there'd be no way to recover the plain text. So there's certainly simple mathematical arguments for why M2 has to be greater than or equal to M1, but hopefully the intuition there is clear that you have to have at least as much information in the ciphertext as the plain text in order to be able to recover the plain text at the other side. So we also talk about the keys. We have encryption and decryption keys, and so I'm assuming that they can be different here. And so we have K sub E is what we call the encryption key space. That's the set of all possible encryption keys that can be used. And these are just, again, binary strings. They're N1 bits long. And so you can think about a key generation step before you start communicating is picking a random key out of the encryption key space, KE, right? So your key, your encryption key comes from this set. Similarly, decryption key, and again, those can be different lengths. Typically, they're the same length. They don't have to be. The one requirement with all these links, M1, M2, N1, and N2, is that they're all polynomially related, right? So you can't have like plain text messages that are exponential in the length of the key. They all have to be related by polynomials. Now they can be large polynomials. So you can have a key space that's 100 bits, and then the plain text messages are the length of the key to the 5th power, right? So then if it's 100 to the 5th, you can go up to 10 to the 10th. What is that? 10 billion bits for your plain text. But again, polynomially related. The two functions then that we're interested in, up here, notice this subtitle up here, the good side. This is, we're not thinking about adversaries yet. This is just what the good guys do, right? We're trying to keep information secret. We're encrypting, decrypting. We're not thinking about adversaries yet. So encryption function, decryption function. The encryption function takes an encryption key, something from this set KE, and a plain text, something from the plain text message space up here, and produces a ciphertext. The decryption function takes a decryption key and a ciphertext and produces a plain text. So for this to be a proper encryption function, you have matching pairs of encryption and decryption keys, so that anything encrypted with an encryption key, take the plain text, get to a ciphertext, we decrypt that with a matching decryption key, we should get the same plain text back, the original plain text, right? So this just defines the functions, what the inputs and the outputs of each function are, and we have sizes now, so we can talk about polynomial time algorithms. Since these are functions that the good guys do, the encryption and decryption functions have to be polynomial time, right? The running time of those functions has to be polynomial time, because we want to be able to efficiently compute encryption and decryption given the correct inputs, right? So these are algorithms that we want to be able to use on a regular basis, and we want to have a secure system. Secure against what? Well, here's the bad side. Here's what an attacker can do. The attacker takes some knowledge they're able to gain, right? So one of the questions you can ask is, what does the attacker know? Generally, they know at least one ciphertext that they have captured. Sometimes they can know more than that. Sometimes they'll know a matching plain text and a ciphertext. We'll talk about that in a second. But the attacker knows some information that comes from a set of data, and that's the information known to the attacker. So this D is the data that the attacker knows coming into it. Then we have what's called a likely message function. Given the information that the attacker knows and a plain text that they're just proposing, right, saying this could have been the plain text, This function, the likely message function, computes a 0 or a 1, saying whether or not that plain text is the correct decryption. So we'll use this in just a second if that's not clear, so you'll see what this means. So that's what the attacker knows. One of the other questions we asked on that original picture is, what's the goal of the attacker? So two things come to mind. The first goal is maybe they want to, right, the attacker sitting there in the middle. There's some plain text message that's being transmitted secretly. And so maybe the goal for the attacker is to recover the plain text, right? That credit card number that was being transmitted. So in terms of our likely message function then, the goal of the attacker is to find a plain text P such that, oh, I've got these backwards. This should be L of D comma P. Given the data that we know and this plain text P, that it's likely that that's the plain text, right? So we're trying to recover a plain text that is the likely message, the likely decryption of the captured ciphertext. So that's one goal we might have for the attacker. In practice, we actually, this is generally the goal that we have, but even more, we make it even easier on the attacker. We say that the attacker succeeds if they get any information at all about the plain text. They may not be able to find the full plain text, but any information at all leaking out of the ciphertext is considered a win for the attacker, right? If they can figure out that the first bit of that credit card number is a 1, then they've discovered something they're not supposed to know. And so that's a win for the attacker. That's how in practice we do things. That's a little bit harder to describe here. So I've put simpler versions on the slide here. A second goal, which is even harder for the attacker than the first goal, would be what we call a key discovery attack. So key discovery is to find a key K, such that when we use that key with our captured ciphertext, we get a plain text back, which is the likely decryption of the plain text that we have, right? So now, instead of just finding the P, right? Earlier, we just wanted to find the P directly. No decryption function involved at all. We wanted to find the P. Here, we're finding a key K that produces the P. Now, that's harder for the attacker to do because you're sort of like one level removed from this, right? You're finding a key that produces P rather than just finding P. If you could do this, you could find the P and you could recover the plain text like this, right? So, so this is harder for the attacker, but it's also much more powerful for the attacker, assuming that the people that are communicating are going to keep using this key. That means that you can very easily decrypt all the future messages, right? Once you figure out the key, any future messages that are encrypted with the same key, you're the attacker, you can just decrypt now that you know the key, right? So key discovery is really powerful if the attacker can pull that off. Here are two different, very specific examples, both of key discovery, but different. So the D set up here is different. What do you know? What does the attacker know? So key discovery with a known plain text attack is somehow or another, the attacker has captured a pair, a matching plain text and ciphertext pair, right? So in addition to knowing a ciphertext, they also know the matching plain text. And then what they want to do is they want to discover the key, right? It's a key discovery attack that was used to create that ciphertext from that plain text. And then I can decrypt future messages. So in this setting, the likely message function is just, right? So this D, the data that we know, includes this pair P1 and C1, right? So P is the likely plain text message if P equals P1, right? So P equals P1, and when we decrypt C1, we get this P, which matches P1. And so we've essentially found the key that was used to create ciphertext C1 from P1. This assumes we have this matching pair, and that makes I think most people's first reaction to that is, well, if I knew the plain text for the ciphertext, then why do I have to break anything? But the answer to that is you've captured one, and you want to be able to decrypt all the other messages, right? So there are lots of examples in practice where this actually happens. This happened as recently and in as high stakes a setting as the time leading up to World War II in military cryptography, where the Japanese used a system called Purple to encrypt. That's what we called it. And so one of the things they would do is the Japanese would send a message, a memo, to be delivered to the US government, right? But they would encrypt it and send it to their embassy. The embassy would decrypt it, and then they would hand deliver that to the US government. And guess what? We captured the plain text. Now we captured the ciphertext when it was being transmitted. They were nice enough to decrypt it for us and hand us the plain text. And now we have the matching plain text and ciphertext. And then there were private messages that they sent as well to their embassy using the same key. And then we could decrypt all of those. So that's a real world example. There are lots of other places where this comes up. For example, and it doesn't, known plain text, you might only know part of the plain text. That's another variation of this. If you send somebody an email, there's a lot of predictable things in email headers. It starts with from, FROM : right? So, and if you know who it's from, you can even fill in their email address. Now you even know more plain text. And so you can use that to help you learn the key, which helps you decrypt the message. So that's a known plain text attack. If you want to give the attacker slightly less power than a known plain text, then you can just assume that they know certain characteristics about the plain text. So a prefix of the message, for example, that it has an email header, or even that it's written in English. If you study, there's an area, a field of study called information theory. And if you study information theory, one of the things that you learn there is that out of all possible sort of random messages that could be sent, the fraction of those that are actually sensible English messages is a really super tiny fraction. And so you can if you decrypt something and it has a reasonable length and it looks like English, that was almost certainly the plain text, right? Just because there aren't very many sensible English messages that could come out of that. Most things are going to turn into just gibberish. And that can actually be analyzed. The same person that actually invented the entire field of information theory created some of the theory behind cryptography. The guy's name was Claude Shannon. And a lot of his work he did during World War II, at the same time that Alan Turing was doing work on cryptography and computers over in England. Shannon was in the US. He worked for Bell Labs. And he did a lot of crypto theory. He did information theory. The work he did on information theory was declassified pretty soon after World War II was over. The crypto work took a little bit longer for them to decide that they could release that. But they're very closely related to one another. And this, the notion of English email messages as characterized by the information content from information theory, leads to a way to build this likely message function to break encryption systems. And one of the measures of that is called the unicity distance, which was invented at the same time by Claude Shannon. There's a lot to this. And so some of these are sort of buzzwords that I know are just going to go straight through you. But there's a lot of cool history to this, as well as the way all the pieces fit together is fascinating. But these are the functions. These are how we define things. And let's see what that means for P versus NP. So we said earlier that encryption and decryption functions are things that we want to be able to do efficiently, right? That's what enables us to communicate securely. So those have to be efficient. From theory of computing, the definition of what it means for something to be efficiently computable is that the time complexity is polynomial. So these are polynomial time functions. The adversary is also a computational process, right? So here was one of the versions of something we had to do. This was a key recovery attack with this likely message function. So we want to find a K such that when we decrypt a captured ciphertext into a plain text, that it's likely that that plain text was the actual message that was sent, right? So that's what the attacker wants to do. They want to find the K. And that's a computational problem, right? I give you all of this stuff over here, except for K. And then you want to know, can you find a K that gives you the likely plain text message? You would like for that to not be efficient. You would like for that to not be polynomial time. And the kicker with this, when you look at it from theory of computing, from complexity theory, is that you cannot have secure encryption like this unless P is different from NP, right? So our big question last week was we defined P and NP completeness and looked at the possibility that P equals NP or P doesn't equal NP. For cryptography to exist, we have to have P not equal to NP. If somebody discovers an efficient algorithm for some NP complete problem, which means that P equals NP, then we would not have any encryption that satisfies these properties. Now, that doesn't mean that we couldn't communicate securely, because we might just relax this condition right here. So we want the attacker's algorithms to be inefficient, and we're using our notion of inefficient as being it's not a polynomial time function. But there are different notions of inefficiency, right? If something takes time into the 100th to break, sure, that's polynomial time, but it's not practical. It's not efficient in a very practical sense, even if it's polynomial time. So I know there are a few of you that are also in the algorithms class. And on your last homework, you're actually sort of exploring that issue. So let's see why P versus NP matters in this case. And so what we'll do is we'll define the following language, the following decision problem. And so D is our knowledge, right? So D, this is the same D as on the previous slide. It's what the attacker knows. And the attacker, in this case, is going to know this captured ciphertext. The attacker also knows the likelihood function, the likely message function, and it knows the decryption function, right? So it knows how to compute these things, and it knows the ciphertext. What it doesn't know is it doesn't know K. So that's all in D. So the unknown is K. And so one way to define a language out of this is that you could say there exists a K such that when you decrypt the ciphertext with the key K, you get plain text that's the likely message, right? So does there exist a K? There are certain settings where that's an interesting decision problem. In most cases, it is not, just because you have an attacker that's intercepting real messages, and the receiver is decrypting those, so you know that there exists a key that decrypts it, right? So the question of whether or not there exists a key that decrypts it, it's a valid question mathematically, but it doesn't come up in the practice of cryptography because there always is a key. So what we do instead is we look at prefixes of this problem, and we make a prefix part of the input, right? So let's say this X is 100 bits long. So we have our captured ciphertext in D. We have 100 bits for a second part of this input, and we're asking, does there exist a key that starts with these 100 bits? In other words, we're not just saying, does there exist a key, but does there exist a key where this is part of it? Now, that's a much different question, right? So in a real setting, we would know that there exists a key, but we don't know what the key starts with, right? So we don't know the first 100 bits. So asking this as a decision question is much more interesting. And in fact, if you could solve this problem in polynomial time, then what you can do is, so if you know a prefix of length 1, so algorithms class people pay extra attention here because this sort of gives you a huge hint on your homework. If you know a prefix of the key that has length 1, you know what the first bit of the key is. There are only, so let's say the first bit of the key is a 1, right? The length 2 prefix of the key can only be either 1, 0 or 1, 1, right? One of those two things has to be a prefix of the key, and only one of them can be, whichever is the correct second bit. So if you know that the first bit is a 1, and you know that you have a polynomial time algorithm to answer this question, then you basically just ask the question twice. So if the first bit's a 1 in the key, you ask, hey, are the first 2 bits 1, 0? And if the answer to that was no, hey, are the first 2 bits 1, 1? That better be yes, because you were assuming that the first bit was a 1. You can answer both of those in polynomial time if this decision problem can be solved in polynomial time. And so now you know what the first 2 bits of the key are. Given the first 2 bits of the key, guess what? In polynomial time, you can find the first 3 bits of the key. Then you can find the first 4 bits of the key and the first 5 bits of the key. So if you can answer this question for any prefix of the key, then you can extend the prefix by a bit, and you can keep doing that until you know the entire key. So if you can answer this decision problem in polynomial time, then you can find the key and you can be a successful attacker. You can break the scheme, right? So that means that you can compute the key. The other important thing about this is that there is a non-deterministic polynomial time algorithm for this decision problem for that language, right? So you've got your inputs, you've got D and X. What do you do? Well, non-determinism, remember, is kind of like magic. It's like the omniscient guide to your computation. And you're allowed to just non-deterministically guess things and see if they work. And if something works, you magically get that. So I'm going to use non-determinism to guess the key K. And then I can verify, once I've guessed what the key is, that X, my input X, is a prefix of K. And given that key K, I can decrypt the captured ciphertext and get a plain text. I can run that through the likely message function and make sure that's the likely message. So once I use non-determinism to guess the key K, then I can verify all of these conditions And that is a non-deterministic polynomial time algorithm for this language. So this language is in the class NP. If I could solve this in polynomial time, then I could break the encryption system. I could compute the K in polynomial time. So this is an NP. If P is equal to NP, then this is also NP. I can do it in polynomial time. Then I can compute the key. Computing the key is breaking the system. So if P equals NP, then I can do a key recovery attack, a known plaintext key recovery attack for any encryption scheme, right? I haven't used any properties of the encryption scheme, just that it exists and it can be computed in polynomial time. So it's not a question of how clever I am in my, designing my cryptography. That doesn't enter into this at all. It's just a question of non-determinism allows me to guess the key and I can verify it. And if P equals NP, then I don't have to guess anymore. That non-determinism is unnecessary and there's a way to compute the key itself in polynomial time. So if P equals NP, cryptography ceases to exist. So, people that do algorithms work and study optimization algorithms, a lot of optimization algorithms, a lot of optimization problems are NP complete. They would love it if P equals NP because then they can solve all their optimization problems very efficiently. Cryptographers panic about the thought that P might equal NP because that would be the end of the world for cryptography, right? We would lose everything that we believe is true about cryptography, and things could be broken in polynomial time. So that's how cryptography relates to P versus NP. That is a place I can pause and see if people have questions. Are there any questions? No. Okay. Well, let's press on. So the second thing to talk about is how do we define security? So we sort of hinted at some ways to do that. So a key recovery attack is one goal for an adversary, but it's really not quite strong enough. We want something that where it's easier for the attacker to do, and if the attacker could do it, then it violates our notion of security. We don't want to require the attacker to compute the key because that's a really hard problem. We want things that are safe against much more lenient definitions of security. So what we're going to do is, instead of talking about encryption for a second, we're going to back off and talk about something that's easier to think about, I think, anyway, and that is random numbers. So randomness is vital to a lot of different kinds of security. And we use random numbers in a lot of places. So there are what we call challenge response systems. So if challenge response actually comes from, it's another military thing. So in general, it came from the days of aircraft. You wanted to identify an aircraft that could have been on your radar. And so what the military aircraft had in them was a challenge response system where it would, it was radio. It would receive a challenge, that's a number, and then it would compute some response that presumably only, that was a secret function that was built into our military planes, and it would compute an answer, and it would send that answer back to whoever was challenging it, right? The radar system that was challenging it. So why is that important? Because if our aircraft are the only ones with those devices that can answer random challenges, then we can identify friend versus foe, right? Our aircraft versus other people's aircraft. And the fact that they were random challenges is because, you're sending out radio signals. Anybody can monitor that. So if it was just a matter of saying, hey, I'm a US, plane, and there was no random challenge involved in that, then as soon as even if it's encrypted, as soon as the adversary can capture one of those messages that says, "Hey, I'm an American plane," they could just replay that all they wanted to, right? So the fact that it is a random challenge makes it change every single time, and the response has to match up with whatever the random challenge was. So the random numbers that go into that, creating the random challenge, that's a place we use random numbers, and it's important that they're random and unpredictable, and that they don't like repeat, right? That's a general version of what we call the use of nonces to avoid replay attacks. So a nonce is basically that random challenge. And a lot of network protocols use nonces to avoid that same kind of replay attack, where if you're authorized because of something that you said, you don't want to reauthorize maybe an attacker for saying the same thing again. It has to match up to a random nonce. So unpredictability in systems, you want to randomize things so that there's sort of a moving target. There's a lot of applications of this just in plain system security. Who's in this class? I don't think anybody is in this class that was in my security class. Maybe Emily. I can't remember if Emily was in the security class. Maybe so. But protecting programs against an attack called a buffer overflow attack requires creating what's called a random canary. And that unpredictability makes it hard for an attacker to get around certain protections. So random numbers are used there. We use randomness for difficult to predict access tokens. When you log into a website and there's something called a session ID that's associated. It's stored in a cookie in your web browser called a session ID. And that's a random string that has to be difficult for an outsider, an attacker to predict. Otherwise, they can do what's called session hijacking. They can take over your session if they can guess your session ID. So anyway, lots of places where we need random numbers. And so let's think about two different ways of generating random numbers. One way is to actually have what's called a true random number. So if you need n bits, then each bit has independent random probability of a half of being a 0 or a 1, right? So if I've got 100 bits, think about somebody sitting there flipping a coin 100 times, heads or tails, and you have to do each bit independently generated, probability 1/2. And that's one way you can, that's sort of the ideal, right? The problem is true randomness is expensive and slow. So computers, by the way they're designed, they're very logical, they're very repetitive. And so the way that computers get true randomness is they'll do things like measure the time between your keystrokes as you're typing down to the microsecond, right? If you do that, the last few bits of that time are basically random. But it's not, right? Computers don't compute randomness. They're measuring some physical process which has randomness in it. They can measure the time between network packets. They can measure the time it takes for a hard disk, the head on a hard disk, to seek to the data that you're interested in. That's much less likely now than it used to be. It used to be, hard disks were physical devices, rotating magnetic platters with heads that actually had to move physical distances. And once you make that a physical problem, then there's a lot of randomness to the precise timing. These days, when you've got solid state drives, SSDs. There's no physical movement, no physical action anymore. And so the time to access data with an SSD is actually very, very predictable. And so if you try to generate randomness from that, it's not going to be random at all. So you're sampling physical processes like somebody typing, and they're not going to be typing 20 billion characters every second, right? So it's hard to generate really long, truly random bit strings, just because you don't have that much true randomness available to you. So what do we do in practice? This was actually supposed to be a little right arrow here because it's a function definition. That's the domain, that's the range. Forgot to go replace that symbol. But this is a pseudorandom number generator. A pseudorandom number takes S bits. We call this the seed of the pseudorandom number generator, and then it computes N bits, right? So N bits that are truly random up here, N bits that are pseudorandom down here, and this is a seed value. So anybody that's ever programmed up like a game before, maybe like you do a little blackjack game, you could do that in 130 or something. I don't know what kind of assignments you had, if you did any games or any randomness, but if you give a pseudorandom number generator the same seed, it will compute the same pseudorandom output, right? So you have to make sure that the seed is different as you play the game over and over and over again, or else you get predictable output. One of the interesting security stories of people that botched a pseudorandom number generator is that they used a pseudorandom number generator that was predictable. It had a small seed for an online gambling site. So it was an online blackjack site. And people analyzed it enough where they could actually predict the pseudorandom number generator that was playing the game, that was dealing the cards out, and they could predict the cards that were coming. And they took that website for a ton of money because they could predict the random numbers. They weren't really random, right? So true random, you would never be able to do that. You couldn't predict it. But a bad pseudorandom number generator that used maybe a seed that was too small, you could do that. There was an encryption system in the original Unix systems back in the 1970s, a program called Crypt that used a pseudorandom number generator that had a seed that was 16 bits long. Then what they did in those days, because that was in the early 70s, we didn't really know a lot about how to make secure encryption then, but we did know that there were some smart people out there. And then this was developed at Bell Labs, which is where they developed Linux. Actually, Claude Shannon that I mentioned earlier, that invented information theory and some of the early cryptography theory, he was at Bell Labs too. So Bell Labs was a private research firm that they invented the transistor, they invented the laser, they basically invented cryptography and data compression. So it was an amazing place, at least up until about the early 80s. I worked there in the early 80s and it just went downhill from there. No connection there, I promise. Anyway, what they did in the early 70s, I guess, a long way. They also, C and C++ programming languages were also invented at Bell Labs. And the C programming language was invented by Brian Kernighan and Dennis Ritchie. And so we didn't know a lot about the theory of cryptography back then, but we knew that Dennis Ritchie was a super smart guy. And so what the Linux developers did was that they would develop these things and they would give them to Dennis and say, hey, can you break this? And so they did this scheme with a 16-bit seed and they gave it to Dennis. He broke it like in a day and he said, no, you need to do better than that. So anyway, fun little story, but and it involves pseudorandom number generators and the seed. A cryptographically secure pseudorandom number generator is not going to use a 16-bit seed, because 16 bits there's only about 65,000 possibilities. And so you can basically run through all 65,000 possibilities and just try them all and see which one generated your pseudorandom stream. And then you can predict what the next bits are going to be. So the way to think about this then is it stretches a small amount of randomness. Now, small, 16 bits is too small, but 128 bits, 256 bits, those are good enough to give you some security. So a pseudorandom number generator can take this small 256-bit seed and stretch it into something that could be billions of bits long. And then we can use that as if there were random numbers, assuming this is a cryptographically secure pseudorandom number generator. Hopefully that's clear. So how would we talk about the security of something like this? Well, now we go back to something else that comes from the 1930s and 40s. But now we go over to England, to Alan Turing, and we look at some of the things that he did. And one of the things that carries his name these days, in addition to Turing machines and the Turing Award in computer science, is something called the Turing test, the Turing test for artificial intelligence. And the basic idea of the Turing test that he proposed, and he called this an imitation game, which is also the name of a movie about Alan Turing that I highly recommend if you haven't seen it. But the imitation game is this idea in artificial intelligence where you have this person out here, he's called the interrogator, right? Somebody who's asking questions, typing in, think of this as a little chat window, just like our chat window in Zoom here, okay? So he's chatting to something over here and chatting with either a real person on a terminal or a computer. Interrogator, right? Isn't that the right word?
Interrogator.
Interrogator. I guess that would be the right pronunciation. What am I confusing this? That's actually interrogator. There actually is a word that's pronounced that way.
Maybe it's just how you pronounce it in British, but usually you call them the interrogator.
Oh yeah, maybe it is just the British pronunciation. And so, okay, that's my excuse now. It's the British pronunciation. Turing was British, so yeah, there we go. All right, so we're chatting with one of these two things. We don't know which, and the idea is that we need to interlocutor. Thank you, Daniel. That was actually the word that was making me pronounce it that way. It wasn't that I was thinking British, but interrogator. All right. So we're chatting with one of these two things back here, either a real person or a computer. And then after chatting for a little while, the interrogator has to guess whether or not they're chatting with a person or with a computer. And if they are fooled into thinking that the computer is the person, or they just can't tell the difference, right? Then that computer passes the Turing test, right? So, whether or not this is a reasonable definition of artificial intelligence is up for debate. I think most people in the past 10 years, 20 years would suggest this is really not the right way to think about what it means for a computer to be artificially intelligent. You got all sorts of counterintuitive things like computers can do, you're thinking about this as how do we make a computer demonstrate human intelligence, but there are also things that computers do really well that people don't do, right? So what is whatever this big number times this big number is? Unless you're asking Rain Man, that's going to take a person a while to answer that, but a computer can do it real quick, right? So the computer, in addition to being able to mimic human intelligence, may have to like dumb down their computational abilities as well, and that seems sort of strange to do. Anyway, that's the idea. It was a very influential idea. There's a contest that's held every year that I don't remember the name of off the top of my head, but there's a contest that's held every year where people create chatbots and they try to do something that can pass this test. And so far, some programs have come close. No program has ever completely won that challenge. Although the past couple of years, they're doing pretty well. But anyway, the imitation game, two options. I don't know which one they are, and an interrogator out here trying to tell the difference is a very, very influential idea that basically changed the face of cryptography when people applied it to crypto. So here's how we apply that to the idea of pseudorandom number generators. So our interrogator out here, this is our adversary from earlier, right? And then on the other side of this wall is either a true random number generator or a pseudo-random number generator. And the adversary, the attacker, has to decide which one of these two they are talking to. Right? So again, it's the pseudo-random number generator is basically imitating a true random number generator. And you want to see if it can do that imitation in a way that the adversary can't tell the difference. So formally, we define this as a game that's played between the adversary and a game master, right? So what happens? The game master picks a random bit, 0 or 1. That bit tells the game master whether they're going to use a true random number generator or a pseudo-random number generator. Okay. So the adversary out here then can ask for some bits. Give me 1,000 bits. And then what happens? If that bit B is 0, then the game master sends, if the adversary asks for 100 bits, the game master sends 100 truly random bits. If the adversary asks for 100 bits and the bit, that secret bit, right? So the game master knows the bit. It doesn't reveal the bit to the adversary. If the bit was a 1, then the game master picks a seed at random and then sends the output of the pseudo-random number generator function using that seed to the adversary, right? Generates the 100 bits that way. The adversary receives that response and has some algorithm, the adversary's algorithm, that processes that and computes a guess, and it tries to guess whether or not the bits came from the true random number generator or the pseudo-random number generator. The adversary wins this game if it guesses correctly which one it was interacting with. So hopefully you see the similarity between the Turing test and the AI game and this. And the benefit of the pseudo-random number generator is that we can stretch a small amount of randomness out to a much larger number of bits, and no polynomial time algorithm can tell the difference. So this is a secure pseudo-random number generation algorithm if no polynomial time adversary can win with probability significantly more than half, right? A half is what you would get if you just took a wild guess, right? If you didn't even look at the bits and just said, flip a coin, I guess that's a true random number generator. Or, came up tails, it's a pseudo-random number generator. You'd be right half the time. So the question is whether the adversary can win with like 3/4 probability instead of half. Then they've done something significant. So this, no polynomial time adversary can. There is no polynomial time algorithm to, right? This algorithm A, there is no polynomial time algorithm A that can properly compute this guess. There is a notion of probability here, so this isn't exactly P versus NP. but it's the same basic idea, right? We're trying to prove a lower bound, a problem that cannot be solved by a polynomial time algorithm. And that's the same kind of argument we do for NP completeness proofs. And so we use reductions for this kind of argument in security, just the same that we use reductions in NP completeness. So one more game. This is what a game looks like for cryptography, right? So this is why the reason we did the random number generator earlier was because it was a much easier problem to talk about, right? It's true or it's random. The game for encryption is actually more complicated because we have an adversary that can do more than just ask for bits. This CPA stands for Chosen Plain Text Attacker. So when we talked about the original version, it was the known plain text attacker. They had a plain text and a corresponding ciphertext. They knew the two. This is a chosen plain text, which is giving the adversary even more power, because what can the adversary do? The adversary can create a plain text here, this query, send this over to the game master and say, hey, what's the encryption of this plain text? And the adversary will compute the encryption with a secret key, right? The game master has picked a secret key and a random bit. It computes the ciphertext and sends that back to the adversary. So now at this point, the adversary knows a plain text that they actually picked and the corresponding ciphertext. So this encompasses any known plain text attack can be used now because I know a plain text and corresponding ciphertext. But this is much more powerful because I can keep asking these. I get to pick the plain text, and I can ask this as many times as I want, polynomially many times, because I have to run in polynomial time. And then at the end of all of these, I can learn everything I can about this, and then I get to pick 2 challenge plain texts, send those over to the game master. The game master picks one of them, right, according to this random bit, encrypts a randomly chosen one of these 2 challenges, sends the ciphertext back to the adversary, and the adversary has to guess which of the plain texts was encrypted. It has to guess that bit B, right? And again, the adversary wins if they guess correctly. And the encryption scheme is secure if there is no polynomial time adversary that can win this with non-negligible probability. That means significantly more than just flipping a coin. This, if an encryption scheme satisfies this characteristic, there is no polynomial time adversary. So if you look at the adversary's algorithm, there's no polynomial time algorithm to break this scheme. According to this game, this is what we call an NCPA secure encryption scheme. Indistinguishability, because that indistinguishable game, going back to the Turing test, CPA for chosen plain text attack, it's indistinguishable under chosen plain text attack. And that's what we mean by a secure encryption system. There are a lot of, this seems like we're giving the adversary a whole lot of power, and we are. And so the point is, if we can be secure against that really powerful adversary, then we can be secure under more reasonable models as well, realistic models. And we have schemes that are secure like this. And so we have some very secure schemes. Last thing I wanted to say, so this is how we define security in games and in terms of polynomial time algorithms, and hopefully reasoning that polynomial time algorithms don't exist for certain problems, for breaking the systems. And so the last thing that we could talk about, and this is where I ran out of slides, but I'm also running out of time, is how reductions come into this. So let me just give you the idea real quick, and hopefully you'll see how this is used. But reductions work just the same as we talked about before. We have 2 cryptographic schemes. This is like your 2 languages when you're dealing with NP completeness. In NP completeness, one language is known to be NP complete, and the other is the one that you're interested in, and you're going to prove that it's NP complete, right? So we've got 2 cryptographic schemes, one that we know to be secure, one that we would like to say is secure. They may be for the same problem. They could be two encryption schemes that we want to relate to one another, or they could be actually for entirely different problems. One pseudorandom number generator and one encryption scheme. We do a cryptographic reduction from one problem, one scheme to another. If we can use, right, we use adversaries over here to create adversaries over here, right? So we use an adversary against this game to create an adversary against the P1 game. And then this reduction, not only does it have to be polynomial time, but the success has to translate. So with NP completeness, we were talking about languages. And so the reduction F, we said that F is in language one, if and only if, X is in language one, if and only if F of X is in language two. Here we're talking about success of the attackers, and that the attacker that we're creating, the adversary that we're creating for P1 has non-negligible probability of success if A does. This succeeds if this does. And then since this succeeds if this does, the logical contrapositive is that, so if this succeeds, then this succeeds. The logical contrapositive is if an adversary can't succeed in problem one, then an adversary can't succeed in problem two. If P1 is secure, then so is P2. And so we can, for example, take P1 as a secure pseudorandom number generator. And we can use the pseudorandom number generator to create an encryption scheme. And then we can prove that if the pseudorandom number generator is cryptographically secure, that you can't tell the difference. No adversary can tell the difference between it and truly random numbers, then the encryption scheme is secure. And there are ways to do that construction. And so given a secure pseudorandom number generator, we can create a secure encryption scheme. Everything in cryptography is relative like this. If we can do A securely, then we can do B securely. And everything has to be relative. Why? Because if P equals NP, nothing is secure. So we can't say that we have a secure pseudorandom number generator. Because guess what? If P equals NP, then there aren't any secure pseudorandom number generators. But we can say that if this is a secure pseudorandom number generator, then we have a secure encryption scheme. And if P doesn't equal NP, then that could very likely be the case. But if P equals NP, then none of it's secure. It all falls apart. So that is the basic idea. That's how P equals NP fits into all of this. This is how we define security with these games and polynomial time adversaries. This is how we use reductions, the same way that we argued about NP completeness, that there is likely not a polynomial time algorithm for NP complete problems. We can argue that there is likely not a polynomial time adversary that can break an encryption scheme. And that is sort of the tour, a very quick tour through cryptography from the standpoint of complexity theory and theory of computing. Do people have any questions about any of that?
I just had a quick note for the slides. You to put them on Canvas?
Yes, I will put them on Canvas. I noticed a couple of typos because I was creating these real quick. I'll go fix the typos, and I will post those in Canvas along with the recording, like I've done with the PDFs in the past. Other questions? Okay. Don't forget your homework. Homework's due on Wednesday. We'll do a review and work through solutions to those if you want to on Wednesday, or answer any other questions you have on Wednesday to prepare for the exam. But that's it. Have a good couple of days.